Let's rethink parameterization like we did derivatives. We'll start with the simplest case first. One parameter object, a curve parameterized by some variable t. So every point on the curve is given by a function of t. Every coordinate is a calc1 function, so I can look at its graph and do calc1 to get my slope. Making the transition into advanced calculus, I want to look at the tangent vector, not the slope. So I take a unit vector in the input, and I get a derivative scaled vector in the output. The input, the number 1, is also the unit vector for the reals. So I have a mapping going from t to R3, going from R to R3. Call that mapping F. At every point, a tangent vector goes to a tangent vector. And these are the mappings df. df at 1, df at 2, etc. These are all linear transformations. In the standard coordinate system, it has a matrix representation. It's a matrix taking R to R3. If I look at the tangent line to the curve in R3, f of 1 to put you on the curve, and the linear transformation to move you along the curve. We thought of this as scaling that vector before. Now we're thinking about it as an input vector, output vector. So this is an affine approximation to the curve. Everyone colloquially calls it a linear approximation because of the tight correspondence between the two. If I call the output vector r, and then I just subtract off that fixed vector for a change of variable, there's my r to r3 linear transformation that's approximating the curve. Now that we've done 1, we can do 2. So I've got a surface in R3, parameterized by 2 parameters. There's the 3 blue curves. Here's the 4 green curves. And the function that takes the parameters to space. T1, T2, my parameter values. The 4 green curves are at fixed T1s. The 3 blue curves are at fixed values of T2. Grabbing a point in the parameter space and 2 unit vectors, I can now repeat what we just did twice. It gives me a tangent vector to the blue curve, gives me a tangent vector to the green curve. So looking at the derivative at that point, I'm taking this 2-dimensional space centered at the point 2, 2 to a 2-dimensional object in 3 space centered at the point f22. Mapping R2 to R3. tangent vector to the parameter goes to tangent vector to the curve. Partial derivatives with respect to t1. Tangent vector on the parameter goes to tangent vector to the curve. And partial derivatives in t2. The transformation has a matrix representation where the columns are these tangent vectors. Notice that the curves in the parameter space are functions of t1 and functions of t2. Taking at t1 and t2 derivatives of those give me those unit vectors. So tangent vectors are taken to tangent vectors. Looking at the tangent plane, scaling each of the vectors, I can reach every point in the plane. So I have two new parameters, tau1 and tau2. I get onto the surface and then move along the surface in the tau directions, getting any other point in the plane. Tau is a vector and r is a point in the plane. Technically it's a vector that points to a point in the plane. There's nothing special about 2. The same construction works for n.